and the number of vertices is 1 plus the norm of this prime. And I'll also mention that I advertise we can do this when S has more than 1 prime. I'm only telling you when S has 1 prime for simplicity. But of course, there's an issue, which is that in some cases that there's more than one type of maximal order, so they're not all isomorphic. And this actually happens in Clifford plus square root of t and in the Clifford plus cyclotomic gate sets. And we can also compile for gate sets such as the Fibonacci anyons and Clifford plus t plus v, which now this is an example where the set S has more than 1 prime. Okay, so going back to step 1, how do we do this approximation? So again, we'll just let S have 1 prime for this discussion. And so the input to our algorithm is we have some quaternion algebra over a number field that's so-called totally definite, which is to say that it has no embeddings into the 2 by 2 real matrices. It only embeds into SU2. And this is just a technical condition that we can probably get rid of in the future. We fix some maximal order in a prime ideal, or some set, but for this discussion it's just prime, or just 1. And so here's our S arithmetic unitary group. And we also fix a quality approximation that we desire. And we fix a z rotation, or an angle, phi, that we would like to do a z rotation about. And I'll add that it's sufficient to just look at z rotations because we can break up any rotation into Euler angles. So to a factor of 3, this is fine, and we only care about constant factors for the purposes of this talk. Okay, so we have our target unitary that we'd like to achieve. And what our algorithm does is it finds a quaternion from this maximal order that we fixed that satisfies 2 conditions. So the first condition it satisfies is that it's epsilon away, or I should say its image under this unitary normalizing map is epsilon away from this target unitary. And the second condition it satisfies is that the norm that it generates is just some power of this prime, L, where L satisfies this equation right here. And so this C is some additive constant that we can pre-compute. And so the idea now is we have a 2-step process for doing this. So what we do is we break the problem up into kind of working on the first 2 coordinates, which corresponds to just looking at the diagonal elements of the unitary. And so what we do is this corresponds to, we kind of phrase the problem as sampling from a lattice point from a convex body that is described by, essentially it comes from, we have this number field and there's an associated number field that's a quadratic extension of it. And this field K is such that you can realize this algebra as a subalgebra of the 2 by 2 matrices over K. It's an F subalgebra. And you should just, if you want, you can just think of K as the complex numbers and F as the real numbers. But really, this is a complex number field over a real number field. And it's a nice type of one called a CM field. And so we do this sampling process. Okay, and then we have to solve an integral norm equation. So again, so here's our sampling. And then when we solve the integral norm equation, there's some extra difficulties that we have to deal with. Because it turns out that integral norm equations can actually be computationally hard to solve. And so if we had an oracle for factoring, we could always solve them. But what we can do is we can actually efficiently check whether or not it's easy to solve. And so what we do is we essentially post-select on easy ones. So there's some, let's say, there's some that we know are hard. There's some that we're not sure. And there's some that we know are easy. So we can basically keep sampling until we find that we know is easy to solve, and then we solve it. And so there's also some extra details and things that we have to deal with in the sense that, so in solving this integral norm equation, what we do is we take these easy instances, and using the LLL algorithm, we reduce these to a constant size instance of a norm equation using LLL, and then because it's constant, we could just solve it. Okay, and let me also just add that when I mentioned polynomial time and everything, really I'm assuming that the field itself is a constant. So various issues with terms of like computing unit groups for number fields and stuff, which we've heard about at various QIPs in the past, are not entirely relevant here, but there's obviously connections. And kind of a last issue is that the performance of the algorithm is in a certain sense conjectural, because our analysis assumes that we can kind of uniformly sample from these points, and it's not quite the case. But we think we can probably remove this conjectural issue, and it's a sort of a technical number-theoretic conjecture that if you want to look in our paper, you can see it. But I'm certainly not going to mention it here. So I think I'm about out of time. So I'd like to thank you for listening. And I'll just mention, just again, so what we have is we have a polynomial time algorithm for epsilon compiling, optimal length circuits that achieve an epsilon approximation of an arbitrary unitary. And epsilon approximating, I meant to write there. So now what we can do that we couldn't do before, at least, is we can approximate now for Clifford plus square root of t, and for Clifford plus t plus v. So we can kind of put all these things together now, and we're able to run approximations for this. And, and many, many others as well, but just to give you some concrete examples. We also have, on the basis of our first paper, we give a very general quaternionic framework for producing these sort of complete sets of gate sets for which you can compile by just doing trial division. And I'll add that sometimes these gate sets really blow up, though. So even for Clifford plus square root of t, I think we need something like 9. And then for Clifford plus the fourth root of t, it winds up being like 56. And it's actually, it's way worse than that. I think there's 56 types of maximal order, so we're not even sure how many it's going to take. We haven't run the computation yet. But future work, I mean, obviously, qubit generalizations are interesting. Multi-qubit is also kind of going to be essential for actually doing, higher order compilations for compiling complete algorithms, and also for studying codes. And really, just I expect there's probably many, many other applications in quantum information theory of this type of machinery. And this is maybe just the first time that we'll hear about this quaternions at QIP, but hopefully not the last. So with that, I'll end. Thanks for listening.
Great, thanks, Jon. Are there questions for Jon? Stephanie?
Yeah, so this is a very stupid question probably, because I actually don't know anything about this problem. So if you want to do in other approximation problems, like I have a function, I want to approximate it, or some simpler functions, it's sometimes beneficial to apply some kind of smoothing to the function.
Mm-hmm.
So is there an analog of this here? Like if I say, maybe I don't take u, but I first apply some kind of smoothing to u, and then I search for a decomposition? I don't know whether that makes sense in this problem.
Well, I mean, it might. I mean, what I'm thinking about is this Hecke operator slide that I showed a while ago.
Yeah.
And that smoothing would be kind of maybe like ignoring the higher moments or something like that, or sort of like a design question or something.
Yeah, so they actually want, like, I guess instead of, for example, ignoring the higher moments, want to apply some kind of nice family with some convolution. So this is actually this is like why I thought about this actually.
Right. Okay. Yeah. I mean, possibly maybe it would help you round off these polytopes or something that we're sampling points from or something, or I don't know. Maybe Vadym would have some further insight on that.
I actually don't have immediate insights.
Oh, sorry.
Yeah, but I guess I'll just leave it what Jon said, and probably I will tell you more. I think a little bit more about it. Like.
I don't know.
Sure.
Other questions, Fernando? Oh, wait for the mic, though.
So sorry to throw the ball a bit out of the field, but there are constructions of composite Paul sequences that allow you to, say, construct a specific unitary and compensate for systematic impersistence in the basis of unitaries that you're using to generate.
Mm-hmm.
Here you're but you can only do this for a finite set of unitaries. Here you're saying that at a certain level you can exactly generate a certain unitaries, and then you use those to do approximation.
Mm-hmm.
Can you say that this same set of unitaries that you can generate exactly might also admit some error cancellation, like composite Paul sequences removing systematic errors?
I'm not entirely sure I understand what you mean by systematic errors. I mean, I think we're assuming we don't have systematic errors, but maybe you're asking if there's a bootstrapping process or something. So in principle, yes, I think, and that's probably one reason to care about compiling for Clifford plus square root of t or things higher up in the Clifford hierarchy. I don't know if that answers your question.
We have time for a few more questions. Are there any others? Viv?
So this is one of the cases where we really care about the prefactors. The scaling it's good to know we're starting from a good scaling, but it's the absolute numbers we're going to need to use.
Mm-hmm.
So you were showing like nice reduction, but 50 only looks good to me if you knew it might once have been 15,000. So how well are you getting the numbers down with, does this give any insight back in the other direction for the kind of gates that the experimentalists should be trying to build so that they're optimal sets for minimal actual total numbers that we might need?
Right. So this constant of 4 is sort of a worst case upper bound, and it's sort of, I'd say it's an active research question to know how far we can be pushed down. And there's a lower bound of 3, which actually follows from some very deep results in number theory called the Ramanujan conjectures, now theorems. So you're not going to get better than 3.
Better choices of gate sets? Are you coming up with better choices of gate sets from this? Can you compare?
I mean, one can definitely do this, and I think that this sort of work is done in our group, but not on papers that I'm on. So probably other people in this room who know more about this than I do, such as Vadym, who now knows the answer, so I can call on.
So it's actually so John was talking about like big O log 1 over epsilon, but actually we actually know we can control prefactoring like in front of log 1 over epsilon. And it turns out that basically there are trade-offs you can play. So if you enlarge your gate sets, you can actually lower this prefactor. And basically, I can actually produce you simply gate sets with as small prefactor as you want, but the price to pay is the size of the gate set for that. That's and basically this kind of prefactors that we control. So there's a kind of that prime ideal that we use to generate. So this is kind of a base of the log. The norm of that ideal is the base of the log. So take big prime ideal, you lower the base of the log, and then there's lower bound of 3 in front of log of that base, and worst case lower bound if you sort of do some kind of adversarial choice of angle that will be 4, and our algorithm does 4 under some number-theoretic conjecture. So basically, we are worst case optimal for the.
Thanks, Vadym. And maybe I can add one more comment to this. One issue is error correction. So as you choose these different gate sets, do you have some natural error correction, or do you need error correction, and how do you error correct some of these gates, if you can? Fernando, one more question?
So I had another question. So normally when we write quantum algorithms, we use some classical gate set and say the Cliffords. So are there known algorithms in the literature that would be written in these B bases, or that would be more natural to write in general?
I think not yet.
Great. So we'll move on to the next talk. Let's thank Jon one more time.
Okay, thanks.